In this video, I want to talk about quantified statements that have more than one variable. You can imagine in mathematics there's lots of situations where we want to study expressions that have more than one variable. In fact, that's where most of the interesting stuff comes. So how do we quantify these statements that have more than one variable? So in some sense, it's kind of the same thing as with one variable. So let's do a few examples. So let's look at example 7.1 here. We have for all real variables a and b. So we're told, for all real numbers a and b. So we're told that these guys are real numbers. So they are elements of Blackboard bold R like that. And then we have our usual open sentence there. So if I want to quantify this is basically saying for all real numbers a and all real numbers b, if x is greater than y, then x squared is greater than y squared. So let's try and write this down. So we want a to be a real number. We want all real numbers a. Oh, sorry, I don't want a. I want the reals for all real numbers a and all real numbers b. So for all a and r and all b and r. So there's our quantified statement here. It's universally quantified. And then we just write down our open sentence. So if x is greater than y, that implies that x squared is greater than y squared. And maybe I'll put a little comma here just to be really clear where the quantified bit ends and the open sentence begins. And one could ask, well, we do have a quantified open sentence now, so that means it is a statement. It can be either true or false. Maybe think about whether this is indeed a true or false statement. And maybe pause the video and think about that just for a second, whether this is indeed true. All right, now that you're back, you've probably tried a bunch of examples to determine if this is true or not, and that's not enough to prove something is always true for all real numbers. So I shouldn't have erased that. For all real numbers, since you'd have to try all of them for it to be true. But in coming videos, we'll learn ways of justifying these for all statements so that you know they're 100% true all the time. This one is indeed true, and we'll talk about how to show that or similar things in a later video. Let's look at the next example here. So what we want to do in this is we want to do three different things. First of all, we want to take this English sentence and express it as a logical formula. Then we're asked to negate it. So tell us the negation of it. And then express the negation in words. So that's a really good exercise. Maybe I'll get you guys to pause the video and at least try the first part. Try to express this statement here. There exist real numbers x and y such that these two things hold. X is less than y, and x cubed minus x is greater than y cubed minus y. So try to express that as a logical formula. Okay, so instead of a universally quantified statement, we have an existentially quantified statement. And there are two of them. We have an x and a y. So we need to say that there exist real numbers x and real numbers y. So we usually write there exists an x that is a real number, and there exists a y that's a real number, such that, and then we have our open sentence here. So we have that x is less than y, and x cubed minus x, let me do it like this, is greater than y cubed minus y. So there is our quantified statement here. We translated this English sentence to this logical formula. All right, well, let's negate it now. And negating this expression, let's call this expression, I don't know, let's call it A, I guess. Negating quantified statements that have multiple quantifiers is very similar to negating them when they just have one quantifier. So what we're going to do is we're just going to negate all of the quantifiers that we have and negate the open sentence. So it's going to be the exact same idea from the previous video. So rather than there exists an x and there exists a y, if it's not true, it means that, well, for all x, or I'm missing an R here, for all x in the reals and for all y in the reals, I really don't need this comma either. Let me get rid of that. Now we'll put my comma in. And I want to negate this expression here. If I called the first bit P and the second bit Q, I have P and Q. And if you remember, the negation of P and Q using De Morgan's laws, well, that's equivalent to the negation of P or the negation of Q. Remember, you have to flip that connective there. So we have that either x is not less than y, so it means that x is greater than or equal to y. That's the negation of x is less than y. If it's not less than, it must be greater than or equal to. Or the negation of q. So instead of a greater than, we'll have a less than. So, or x cubed minus x is less than or equal to y cubed minus y. And remember, if you're negating a greater than, it's a less than or equal to. Remember, you need to cover all scenarios. So if it's not greater than, it could be equal as well. So it's less than or equal to. Now, try and write this in words. What does this mean? So pause the video now and see if you can come up with the negation here in words. Write down what this means in words. Okay, what I have come up with, well, we have a double universally quantified statement here. So we'll say for all real numbers x and y, that will be that part. So for all real numbers x and y, so that is that bit there. Now let's write down the open sentence. So I didn't want to say it's not true that this, because that's kind of cheating in some respect, since it isn't simplified enough to kind of be very useful for us. So we did that simplification here using De Morgan's laws. So we can say, indeed, that for all real numbers x and y, we have that x is greater than, in fact, I guess it's fine to put some mathematical notation in here. That's fine. We just won't use logical. So x is either greater than or equal to y, or x cubed minus x is less than or equal to y cubed minus y. And maybe it's instructive to ask yourself, well, which one of these is true? The original statement or the negation? So maybe pause the video now and think about that. Try some examples, play around with this, see if you can determine which you think would be true. Okay, so it turns out that the original statement is indeed true. And let me give you, so this is true here, I'll just mark a little t, and let me give you kind of an example that shows that this is true. Remember, all it says here is that there exists an x and exists a y, so that this is true, that p and q is true. So the ones that I've found are maybe x is 0 and y is a half. And if you plug these in, you can automatically see right off the bat that 0 is less than a half. So we have p is true here. This is p is true because x is indeed less than y. We just need to show that q is true as well. So 0 cubed minus 0 is, of course, 0. And a half cubed minus a half, well, that's going to be 0 cubed minus 0 is, of course, 0. A half cubed is an eighth, and an eighth minus a half is 4/8. 1/8 minus 4/8 is negative 3/8. So you can see here that 0 is now greater than negative 3/8. So here we have q is true as well. And remember, we just needed to find one situation. There exists an x and a y, which we did find. So now, let's do a few more examples. Let's scroll down here. So you'll notice something different with these. The first one, it's doubly quantified. You have two integers, you have an n and a k. But the quantifiers aren't the same. Here is an existential, there is, and here is a universal for all. The second example will be similar. So pause the video now and try to write this as a logical formula. Okay, so let's try this ourselves. So there is an integer n, so this is a existential. So there is an integer n, so we need to say there exists an n, that is in the set of integers. There is an integer n, that is this part is this part, such that, and I'll talk about such that a little bit, The usual rule, this word such that, it usually comes after, if you see this expression, it usually comes after existential quantifiers. So there is an integer n such that, and now we're going to have our second qualifier for all integers n. So let's do that for all integers, or I should say k, not n, for all integers k. So for all k that are integers. So that is our second quantified statement. I'll highlight this one in yellow. So for all integers k, that's that. And then, well, our open sentence is pretty easy. N times k is less than or equal to 0. So that's the first part. The second thing we want to do is we want to negate this. Again, let's call this A. I'm just picking the letter A. You could pick whatever name you want to give this statement. I just called it A. Let's figure out the negation. And maybe it's instructive, before I do it, let's think about this. So if I tell you there is an integer n such that for all integers k, something is true, and you said, no, that's false, how would you say that it's false? What is the negation? What is saying it's not true that this is true? How would you word that? So pause the video now and think about that. Okay, now that you're back, well, if I said it's false that there is an integer n such that for all integers k, something happens, well, that must mean that this isn't true. So for all n, you can find an integer k such that the open sentence isn't true. So to negate this, all we're going to do is we're going to flip both quantifiers. So this is going to be, for all n that are integers, there is an integer k where nk is not less than or equal to 0, so it's greater than 0. And to write this in words again, pause the video, give this a go yourself. I would write it as follows. For all integers n, there is an integer k such that, since we finished our existential quantifier here, there is an integer k such that n times k is indeed greater than 0. So that would be how to express the negation in words. And again, it's instructive to ask yourself, which is true? Is the original statement true? Or is the negation of the statement true? Is it true that there is an integer n, such that once you find that integer, it doesn't matter what the other integer is? If you multiply n times any integer, you get something less than or equal to 0. Or is it true that no matter what n you pick for all n, you can always find an integer k, there is a k, depending on n, where n times k is greater than 0. Which of these is true? And if you think about it, well, there is in fact only one integer that satisfies this. And the key is because it can be less than or equal to 0. And we know 0 times anything equals 0. So if we let n equal 0, k can be whatever, then this equals 0. So this is true. And again, we'll show how to prove this in more detail in the coming videos. But basically the idea is that if n is 0, then we know that 0 times k is less than or equal to 0, since it equals 0 for all k. We know that's true. And since we have a statement being true, the negation of it is false. It's not true that for all integers there is an integer where n times k is greater than 0. Again, if n was 0, then you couldn't find a k to multiply by 0 to get something positive, because 0 times anything is 0. So there we go. Let's look at the next example here. Again, you will see two quantifiers. We have for every positive even integer n. We're going to have to be a little careful about this. In fact, there's 2 ways to go, but we'll just talk about kind of one way right now. There exist primes p1 and p2, so here is our other quantifiers. In fact, there are 2 here kind of hidden. There exists a p1 and there exists a p2, such that, you see the such that because we just finished talking about existential quantifiers, such that n plus p1, or n equals p1 plus p2. So before we go ahead and write this, well, we have a few different sets here that our variables belong to. So we have these positive even integers and we have primes. So let's kind of define those sets. So positive even integer, I'm going to come up with the notation E plus. Why not? Let's call this set E plus. E for even, plus for positive. And that's going to be the set of all integers. So it's things that are integers such that, and maybe this is a good exercise for you, how do I write x is a positive even integer? How do I write that x is positive and even over here using set builder notation? So try that. Okay, now that you're back, well, we could even just say the following thing. So we can say that such that x is positive, so x is greater than 0, and x is even. So we can say, and for our purposes, we'll just say here, and x is even. In the coming videos, we'll really explore how to write down even and odd integers in a nice way that really explains what it means to be even and what it means to be odd. So here's the set E plus. It's a set of integers with the condition such that your integers are positive, they're greater than 0, and they're even. So that's the set of positive even integers, and we need primes. So the set of primes, oh, I have my colon in the wrong place here. My mistake, guys. It should be colon equals, not equals colon. I always put the colon by the name of the thing. So I'm calling this set E plus. It has the name E plus. And let's use, I'm using P for logical things, so maybe P is a bad name. Let's use a curly P. Let's use something like this. This will mean the set of primes. Why not? Some sort of curly P. So that P is going to be the set of primes. So again, for our purposes, we can just say it is natural numbers such that x is prime. So we define these two sets. We have our positive even integers. We have our primes. Now we can go ahead and write this. So we have, for every positive even integer n, so again, let's call this expression a. So for every positive even integer n, so for all n that is a positive even integer, so it's a member of the set that we defined, e plus, there exist primes p1 and p2. So there's kind of two ways to write this. I'll write it out the long way first, and then I can talk about another way that some people write it. So there exists a p1 that is a prime, and there exists a p2 that is prime, such that n is p1 plus p2. Now, some other people, especially when you read mathematics a little more, they'll kind of combine these guys. Since it's the same quantifier, just saying there are two primes part of this set. So you might see some other people write, there exists a p1 and a p2 that are primes. You might see that notation for that as well. So kind of combining those two variables into the same quantifier. Okay. So we have that here. We have our quantified statement. So for all even integers n, there exist a p1 and a p2 that are primes, such that n can be written as the sum of two primes. And I want to point something out here. The order, in some sense, is important. Maybe before we talk about negating it, I'm going to do a little aside here because it is important. Order of quantifiers is important. And let me explain how. The reason is that once you introduce a variable, the other variables that are defined can be based off of the one you've already defined. They can depend on the one you've already defined. So later variables are allowed to depend on earlier ones. And let's say later defined variables. Let me put in defined here. Later defined variables. So what this means, so let's say I picked an n here. If this was true, then this would hold for all even integers. So let me pick one. I'm going to pick 10. Let's say n was 10. I'll just write this down here. N is 10. Now that I picked n is 10, this is saying that there exists a p1 and a p2 such that n is the sum of these, p1 plus p2. So I'm allowed to choose what p1 and p2 are based on something already defined. So it can be based on n. So here I have n is 10. So I'm allowed to pick my p1 and p2 however I want depending on n. So here I could say p1 is 3 and p2 is 7. They're both prime numbers. And then this is true for this particular value of n, since 10 equals 3 plus 7. So order is important here. All right, now that we talked about that, why order is important, let's continue on with the problem. Try and negate this. Again, think about our rules for negation and give it a go. All right, now that we're back, let's go ahead and do this. So, the negation of A, well, we're going to flip our quantifier. So if this isn't true, that must mean there's an n where this doesn't hold for. So there exists an even integer n such that for all, and I'll kind of use this combined notation, for all primes, P1 and P2, that are in the set of primes, that the open sentence is false. So to negate the open sentence, well, if it's not equal to, it's not equal to. So n doesn't equal P1 plus P2. So that's the negation there. And let's write this in words. So there is an even integer such that, and I'm going to write this a little bit differently so it's not in order, but it means the same thing. So I'm saying there's an even integer that can't be written as the sum of two primes. So such that it cannot be written as the sum of any two prime numbers. So there is this in words. And again, I'm kind of changing the form a little bit to be more readable. So I could say, if I wanted to, there exists an even integer such that for all P1 and P2 that are primes, so for all two primes, n isn't the sum of those primes, but it's probably a little more readable in English to read it as there is an even integer such that it cannot be written as the sum of any two primes. Okay, so again, as our little exercise, which is true? A or the negation of A? Pause the video, think about it. Okay, now that we're back, in fact, and this time the negation is true. In fact, this guy is true here since, well, if n was 2, I can't write 2 as the sum of two prime numbers. There's no prime number smaller than 2. So there's no way I can write 2 as the sum of two prime numbers, no matter what prime numbers I pick. So for all pairs of prime numbers, it's not going to be, the sum of them is not going to be 2. Of course not. And the same thing holds for 4. 4 is another, we call it a counterexample. But here's the thing, and I'm just going to talk about this, and because it's kind of interesting. If you change this expression to say that for every positive even integer, if I wrote instead that there was an extra condition that's greater than 4, if we wrote that, then imagine we updated what A and the negation of A were to include that, then we don't know which is true yet, A or the negation of A. We don't know if you can write every positive integer greater than 4 as the sum of two prime numbers. We just simply don't know. In fact, that's called Goldbox Conjecture. This mathematician named Goldbach conjectured that it's possible. We've never been able to find a counterexample. Every positive integer that we've tried, we cannot show that it's impossible to write as the sum of two primes. We can't show that. So we can't prove that this is false. We can't prove it's true either. We simply don't know yet. It's a very famous and very active problem in mathematics. And that's the idea of negating quantified statements that have more than one quantifier, and in fact building them as well. So hopefully you found this helpful. These type of statements come up in mathematics all of the time.